Everything around you is made of fields. Yes, fields. Not grass fields, not football fields, invisible fields that fill all of space and time. According to modern physics, the universe is basically a giant collection of fields layered on top of each other. There is an electron field, an electromagnetic field, quark fields, and several others quietly doing their job like unpaid interns of the universe. All of them exist everywhere at the same time. Now here's the first surprising idea. A particle is not a tiny ball. If you're imagining electrons as little marbles flying around, physics has filed a formal complaint against your imagination. A particle is an excitation of a field. An electron is just a ripple in the electron field. A photon is a ripple in the electromagnetic field. So particles are not little objects wandering through space. They are disturbances, something deeper. Now quantum mechanics makes things even stranger. If nothing is recording a particle's position, nature does not assign it a single exact location, which means it is not secretly hiding at one point waiting to jump out and yell, "Surprise!" And it's not traveling along a neat classical path like a tiny GPS control bullet. Instead, it is described by something called a wave function. The wave function tells us the probability of finding the particle in different places. So instead of one location, you get a spread of possibilities. Maybe a high chance here, a lower chance there, almost zero chance somewhere else. The particle basically looks at that location and says, absolutely not. This situation is called a superposition. The particle is not following one single path from A to B. Instead, the wave function spreads across many possible positions, and these possibilities can interfere with each other. Some possibilities change each other. Others cancel each other out. It's like the universe is running the world's most complicated group project, and half the possibilities are sabotaging the other half. This creates patterns like the famous double-slit experiment, where particles behave like they are arguing with themselves about where to go. Physicists looked at this and said, interesting. Everyone else looked at it and said, excuse me, what? Now let's see what happens when the particle interacts with other fields. Imagine an electron moving through space. It's an excitation of the electron field. At the same time, space is filled with the electromagnetic field, which is never really off. It's like the one friend who somehow ends up involved in every conversation. As the electron evolves, its quantum state becomes linked with the electromagnetic field. Different possible positions of the electron affect the electromagnetic field differently. So each possible position leaves a different fingerprint in the field. This process is called decoherence. Decoherence does not mean the wave function disappears. It means the different possibilities stop interfering with each other. They can no longer influence one another. In some interpretations, these possibilities can be thought of as evolving into separate non-interfering branches. At this point, the quantum system starts behaving much more like a classical object. Now the moment of truth. When the electron finally reaches a detector screen, only one location is recorded. Only one dot appears. Not 10, not 5, not all of them, just one. If we repeat the experiment thousands of times, each electron produces only one dot. But together, those dots form the interference pattern predicted by the wave function, which is slightly suspicious. Individually, everything looks random. Together, everything follows beautiful mathematical rules. It's almost like the universe knows exactly what it's doing, and it's refusing to explain itself. And this leads to one of the deepest questions in physics, not only for electrons, but for any quantum particle in a superposition. When a field interacts with a particle in a way that records information about its position, we observe only one outcome on the screen. One dot appears, but quantum theory still describes many possible outcomes before measurement. So the question is, why do we experience only one result per experiment? And what happens to the other possibilities? Physicists have been arguing about this for more than a century, which is impressive because physicists normally argue about everything. Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says the wave function collapses during measurement. The many worlds interpretation says all outcomes continue in separate branches. Bohemian mechanics says particles always have defined positions, guided by quantum wave. Objective collapse theories propose that wave functions physically collapse under certain conditions. So far, all of these ideas agree with every experiment you can perform. What they disagree on is what is actually happening underneath the mathematics. What we do know is this: at the deepest level currently known, reality appears to be made of fields. Particles are excitation of those fields. Quantum systems are described by wave functions. In the classical way, we experience emerge from underlying quantum possibilities. More than 100 years after the birth of quantum mechanics, we still know how to calculate the outcomes, but we are still arguing about what the calculation actually means. And honestly, the math works so well that it refuses to explain itself. If your brain is still okay after this, like and subscribe for more mind-bending videos. In somewhere in the multiverse, another version of you just subscribed, another unsubscribed, and another is currently arguing about in the comments.